Very good morning. What we have done in the previous lectures is we have talked about when you will say a function is Riemann integrable. Okay, the necessary condition what we learned was is function is bounded on a closed interval a to b, and we are talking about the real valued functions. Okay, so the necessary condition is f is bounded. Okay, and then we have created a partition p, a random partition. So x naught, x1, and so on xn. So they may be equidistant or they may not be equidistant. Preferably equidistant is there. Okay, and that you will also see why it is so maybe soon when we will talk about the criteria for Riemann integrability, proving that is okay. So we have a partition P, then we have defined the lower sum LFP as summation k is equals to 1 to n small mk delta xk. And these notations you are all are familiar. Small mk is infimum of f of x such that x is inside the ik. And what is ik? So you have this is xk minus 1 to xk. This is arbitrary. And what you have defined u as summation k equals to 1 to n capital Mk delta xk, where capital Mk is supremum of this above set. Okay, and all these things are exist. Okay, so all these things and some small mk and capital Mk will exist because of the boundedness of the function. Okay, then we have also shown that so if you have the partitions P1 and P2 such that P2 is a refinement of P1, then we have this LFP1 is less than equals to LFP2 and UFP1 is greater than equals to UFP2. And we have shown that this lower sum, when you consider the sequence of refinements, okay, of a certain partition, so it's going to be monotonically increasing, the lower sum, and the upper sum is monotonically decreasing, and both of them are bounded, so they are necessarily converges. So, and then you can refer the result known as monotone convergence theorem, so which says that if you have a monotonically increasing sequence and if it is convergent, that it converges to the supremum of that set. Okay, similarly, if you have decreasing, if you see monotonically decreasing sequence, then and it is convergent, then it is going to be converges to the infimum of the set. Okay, right. So those limit we have defined as capital L of f and small u of capital U of f. So these are also will have some meaning because of the boundedness of the function. Okay, so these all things are we have shown. So L of f is the supremum of L of fp such that p is any partition of the interval a to b. Okay, and u of f is defined as infimum of u of fp such that p is any partition of k. And we have seen the relation between them as L of f is less than equals to u of f. So then we say that f is, we say that f is Riemann integrable over the interval a to b if these things L of f is equals to u of f. Okay, so if this happens, then we will say that it is Riemann integrable, and these values are denoted by integration a to b f of x dx, the limit. Okay, right, and this is lower Riemann integral. So these are notations, right, with where you will have put bar under a for L of f, and u of f you will put the bar above b, then it will call respectively lower Riemann integral and upper Riemann integral. Okay, so these results already has shown, and I have left an exercise for you, something like scalar multiple of a Riemann integrable function is Riemann integrable. Okay, if a function is Riemann integrable over the entire interval, so it will also be Riemann integrable over the any partition of it. Now, if you go back and check the supremum and infimum definitions, let epsilon greater than 0 be given. Okay, then there exists a partition. What I'm saying is this is there. So there exists a partition P1, you can say, okay, of AB such that L of FP1 is greater than equals to L of F minus epsilon by 2. Epsilon or epsilon by 2, that you can, that's fine, minus epsilon. So L of F minus epsilon, no more the upper bound of the set. And there exists a partition, so that will follow up by the supreme definition, that will follow up the partition of P2, say, of closed interval AB, such that u of Fp2 is less than equals to u of F minus epsilon. Okay, so now, but we want to use the relation of L and U somewhere. Okay, so what we can do here is we can consider a new partition, let's say P3, which is nothing but the P1 union P2. So this will be a refinement of P1 and P2 both. So we have seen, and we will use the result that L of Fp3 is less than equals to U of Fp3. Okay, and so once this P3 is a refinement of P1, okay, so P3 is a refinement of P1, so that will give you the following. So P3 is a refinement of P1 and P2 both. So this implies L of Fp1 is less than equals to U of F, sorry, not U of F, so I'm just, so L of Fp3, because of the monotonicity of the lower sum, which is really less than equals to U of Fp3. For any partition, this result holds true, and which is going to be less than equals to U of P2. Right? So what it gives you, so this will implies, so L of Fp1 is greater than equals to L of F minus epsilon, less than equals to L of Fp3, less than equals to U of Fp3, which is less than equals to U of F minus epsilon. Okay, so this will hold when this implies U of Fp3, let's say, minus L of Fp3 is certainly less than equals to u of f minus L of f. This is, see, this minus this is less than equals to this minus this. Is that you can prove. Okay, so this is u of f minus L of f. Because of its infimum, that's going to be plus epsilon here. So plus epsilon here it will be, and this is going to be plus 2 epsilon. Okay, so if f is Riemann integrable, this is must be true. So u of f is equals to L of f. Okay, so when you have u f equals to L of f, this is 0. Okay, yeah, start with, so this will give you u of f(p3) minus L of f(p3) is less than equals to f2 epsilon. So this is true for every epsilon bigger than 0, and you can get in for every epsilon, you will be able to get the partition P. So in case when f belongs to Riemann integrable AV, then you have u of f is equals to L of f. Okay, so this implies u of fp3 minus L of fp3 is less than equals to 2 epsilon. So for for given epsilon bigger than 0. So this is a one way already has been established now. Conversely, let for every epsilon there exists a partition P of I such that this u of fp minus L of fp is less than epsilon. Now since this u of f is less than equals to u of fp, okay, and L of fp is less than equals to this is less than equals to L of f. Okay, so what can you tell about u of fp minus L of fp here? So you can just greater than equals to here. Okay, so that will implies u of f minus L of f certainly less than equals to u of fp minus L of fp, and which is less than epsilon, and this is 0 is less than equals to. Okay, so this implies this is true for every epsilon. So this is only possible when u of f minus L of f is 0. Okay, because now it is independent of partition now. Okay, so that will shows that u of f is equals to L of f, means f is Riemann integrable. This is known as Riemann's criteria for integrability. So, but if you note that here it is saying there is a partition P of I such that this happens. So it is not possible to many times to establish this result. So what the corollary of this is very important, that if you consider the sequence of partitions, okay, so for given epsilon, so you can start with epsilon equals to 1 by n. Okay, you can start with epsilon equals to 1 by n greater than 0. Then you will means if f is Riemann integrable if and only if this happens. So if for epsilon equals to 1 by n greater than 0, so you take a partition Pn. Okay, and then if you show that u of fpn minus L of fpn is less than 1 by n, then if you limit n tends to infinity, you know that limit of 1 by n is 0. Okay, so that will give you some another criteria, you can say sequential criteria of proving that f is Riemann integrable. Okay, so here you can start with, you can instead of epsilon and arbitrary epsilon, you can work with the epsilon equals to 1 by n. So for each n, you will have a partition Pn, you can say, and you have this is UFPn minus LFPn is equals to this is 1 by n. And this is certainly 0 less than equals to this. So sandwich theorem here, it will proves that limit of u of fpn minus L of fpn is equals to 0. That will give you the guarantee that f is Riemann integrable. Okay, right. So this is the here sequential criteria, you can say. So which says that let I is a closed interval AB and let F is bounded function on the interval, closed interval I. So if you Pn is a sequence of partitions of I, such that this happens. So limit of U of Fpn minus L of Fpn is equals to 0. Then F is Riemann integrable on I. And the limit of UFPN is equals to limit of L of FPN. Because why? Because both of the sequence converges, right? So X minus Y. So you can apply the algebra of the limits. Okay. So then you can show that this limit of NU of FPN is also equals to limit of NL of FPN. Okay. Then only this possible, because both of the sequence converges. Okay, and then these limits, any one of the limit is denoted by that integration a to b f. Okay, so this limit n actually goes to the u of f, and this goes to the L of f. Okay, so this is why we have also considered in the Thomas function, when we try to establish the Riemann integrability of Thomas function, we have considered the sequence of partition. So by considering the equidistant points, so we you can start with x0, x1, and so on xn, where you can x0 is equals to a, xn is equals to b, and if you have xk is equals to x0 plus k time h. So what is h is? H is the step size. You can make it equidistant. That is going to be b minus a by n. Okay, so which will give you the equidistant part, means the partition of equidistant points. Okay, and then depends on the nature of the function. Okay, so the nature of the function is continuous, or if it function is monotone. So now you can work with polynomials, you can work with a sine function, you can work with cosine function, means the elementary functions you can work with to show that those functions are Riemann integrable on I. So now you can finish the problems in your assignments. Okay, so we have already used this criteria in the previous, means like we have also, if you recall, we have also shown the area of the curve bounded by x square, okay, between the interval 0 to b. Okay, there also we have looked at this sequential criteria only in some manner, you can say. Okay, right. So this is the more favorable result for establishing the Riemann integrability of certain function. Okay, then the previous one, because in the previous case the partition is arbitrary. Okay, and it is not able, may not be able to possible to get such partition for a given epsilon. Okay, so that's why this has some advantage here, sequential criteria, so you can use those. Okay, right. Now means like for example, let's do it. So let's consider this example. Okay, this function is nature is continuous and it is monotonically increasing. Okay, and we want to show that function is Riemann integrable. Okay, right. So first let's consider the partition P, which is x0, xn. So we can denote it by p suffix with n as well, because for different value of n it is different, so it will define a sequence of partition. So now x0 is equals to -1, xn is equals to 1, xk is equals to x0 plus kh. So what is h here is b minus a by n. So that is going to be 1 minus -1 by n, that is equals to 2 by n. Now ik is the kth subinterval, that is xk minus 1 comma xk. Now small mk is infimum of f of x, such that x belongs to ik. Okay, so function is increasing. So the infimum will be attained at the left hand point of the interval. That is nothing but xk minus 1. Okay, that is means minus 1 plus k minus 1 times 2 by n. And similarly, capital Mk will be minus 1, so xk, okay, the right hand point of the interval, that is going to be minus 1 plus 2k by n. Okay, so now, and what is delta xk is, you have, this is delta xk is nothing but 2 by n. The length of each subinterval is h. Okay, now what is L of fpn? That you can certainly find out. So that is equals to summation k is equals to 1 to n small mk time delta xk. So that is minus 1 time 2 by n, so minus 2 by n plus k minus 1 time 2 square is 4 by n square. Okay, so now this is equals to minus 2, right, minus 2 by n, and summation k equals to 1 to n. So if you apply the summation over here, so it is 1 plus 1 plus 1 plus and so on n time. So that will, n will get cancelled here. And for this case, plus 4 by n square summation k equals to 1 to n time k minus 1. So you are starting with 0 plus 1 plus 2 and so on till plus n minus 1. Okay, so sum of n natural numbers. So, but the nth term is here is n minus 1. So you know n into n plus 1 by 2. It's a sum of the 1 plus 2 and so on n. So, but here n is n minus 1. So that you can now, so this is going to be minus 2 plus 4 by n square. So you have, this is n minus 1 into n by 2. So that is going to be this. So this is going to be minus 2 plus, so 1 n will get cancelled. So you have, this is 1 minus 1 time 2 is also there. Okay, now this tends to 0 as n tends to infinity. Right, because this is a constant sequence minus 2. So this tends to minus 2. And now 1 minus 1 by n will tends to 1. So minus 2 plus 2 will tend to 0. Similarly, you can now, instead of k minus 1, now instead of this, you are going to have k here. Okay, everything will remain same in parallel. And you can show that u of fpn also tends to 0 as infinity. So limit of u of fpn minus L of fpn will also tends to 0 as n tends to infinity. So by the sequential criteria, okay, you can show that, I mean, you can claim that that function is Riemann integrable. Okay, so similar, u of fpn tends to 0 as n infinity. So this implies the limit of u of fpn minus L of fpn tends is equals to 0. Okay, so this implies that limit of n u of fpn is nothing but the integration a to b f of x dx, and but a is at minus 1 to plus 1. Okay, and that is equals to 0. Just how we have shown. And we have also known that analytical result also 0. Okay, so similarly, you can work with a problem like a function x square. This function is depends on which interval you are talking about. Okay, minus 1 to 1 or positive side or negative side, because the derivative is 2x. Okay, so which will be negative if x is negative and which will be positive if x is positive. For x cube, 3x square, it doesn't matter which side interval you take, it will always be increasing. Okay, and similarly, you can work with the e to the power x. Okay, so e power x derivative is e power x, which is also greater than 0, so it is always an increasing function. So you can work with this also. Okay, and so on. Okay, right. Now, the next result is a very important result, which you can also state in your assignments or somewhere problems, that is if a function is continuous or monotone, either monotonically increasing or decreasing on a closed and bounded interval AB. So that is what important. Function may be continuous, but the interval may or may not be bounded. Okay, so the necessary condition is function must be bounded. Then only you are attaching some another properties, that if f is either continuous or monotonically increasing or decreasing on that interval, then f is Riemann integrable. So that I can left as an exercise. So for monotone, for monotonically increasing or decreasing function, you will proceed in the same way what you have done for this function of x is equals to x only. Okay, so in the similar manner, because for the monotone case, if it is increasing, the mk is left attained at the left hand point of the interval, and capital Mk will be at the right hand point of the interval, and use the fact that this is a monotone function and it is bounded. Okay, then you can show that limit of u of pn minus L of fpn is equals to 0, is equals to 0. Okay, for continuous function, again, you will use the fact that function is continuous on a closed and bounded interval I. So certainly it attains its absolute maxima and minima. Okay, so that will give you some insight of the proof in the similar manner as you have done for monotone. Okay, so that I can left as an exercise for you. Okay, right. So if a function is continuous or monotone, so then you can straightforward say the function is continuous, or function is continuous on a closed and bounded interval AB. So it must be Riemann integrable. So you can state that result. Okay, but wherever it is told that you have to you have to use the Riemann integrability criteria, suppose it is a problem, you have to use that. Okay, you have to use the sequential criteria at least. Okay, right. Okay, right. So we denote the RAB as a class of all Riemann integrable functions on closed interval. Okay, we have also seen function may not be continuous. Okay, but still it is Riemann integrable. Okay, so there are certain functions which are continuous everywhere except at finitely many points. Means only finitely many points are there where the function is become discontinuous. So such functions are also Riemann integrable, that you can also look at the result here. Okay, look at the result that, okay, that will be, you can able to prove in a similar manner by breaking into the interval into, and means like where suppose the function is not continuous or at point C, somewhere in between A to B. Okay, so then you can break the interval A to C and C to B and start working with. Okay, and then means try to, okay, and try to establish the result. Okay, or at least look at the proof of the result in the book. Okay, the proof is not necessary for, means like it's only for understanding. Okay, so now this is the very important result of this you can say integral calculus. Okay, and so which is there are two forms. Okay, the first form is here. So let f be a Riemann integrable. So there are certain conditions. Okay, so f be a Riemann integrable function. So that's very first condition is f belongs to this class R of AB. Then second condition is you have defined an indefinite integral f of x. Okay, so there is right now there is no more condition attached. F of x is equals to defined as integration a to x f of t dt. Okay, then capital F is continuous on closed interval A. So certainly this will be implies, so f is continuous. So just now you have seen, okay, Sorry. So just now you have seen if a function is continuous on a closed and bounded interval, then it is Riemann integrable. So F is also, capital F is also Riemann integrable. Okay. Now, if F is continuous at x naught, so if you attach this one more condition here, if F is small f is continuous at x naught, then you can show that capital F is differentiable at x naught. Okay. So that second here is F is continuous at x naught. Then capital F is differentiable, becomes differentiable at x naught, and it becomes the antiderivative, you can say, for the given function f. So then f dash of x naught is equals to f of x naught. Okay, so to prove this that f is continuous on closed interval ab, how do you proceed? Okay, so that is you have let's say you have for continuity, so you have the defined, so you have the function definition is f of x is equals to integration a to x f of t dt. Now let x naught belongs to closed interval ab. Okay, then what is f of x minus f of x naught? So if f is Riemann integrable on a to b, so it is also integrable on a to x naught and x naught to b. So this you can certainly find out. So this is going to be a to x minus integration a to x naught f of x dx. Now you can work with why x is less than x naught or x naught is less than x. So certainly I can break it down. So let's say you have this is and you have this is going to be x naught is inside, you can say x naught is less than x. Okay, so then you can break this here, a to x naught and x naught to x. So a to x naught will get cancelled. So what you will remain with is x naught to x f of x. So f of t dt you can do with it, no problem. Okay, so this will be magnitude. So if x naught is greater than x, what you can do? So then you can break this interval a to x and x to x naught. Okay, then you will have with minus sign here, but magnitude will take care of it. Okay, and we have also shown that this is less than equals to integration x naught to x time mod of f of t dt from the previous lecture exercise. Now f is bounded, so certainly this is less than equals to m time integration x naught to x dt. So that is nothing but is equals to, you can say, less than equals to m time mod of x minus x naught. Okay. So now whenever this is less than delta, you can create an artificial epsilon that this is entire thing will be less than epsilon. Okay. So epsilon will be delta by m, you can say. So for every epsilon bigger than 0, there exists a delta such that mod of f of x minus f of x naught is less than epsilon whenever mod x minus x naught is less than delta. So epsilon is depends on delta by m. So you can create that. So that shows that f is continuous. Okay, so that shows that f capital F is continuous function on closed interval AB. So this x naught has been chosen arbitrarily. Okay, so that can be worked out. Now, if you attach the part that if f is continuous, okay, small f is continuous at x naught. So if you attach f is continuous at x naught, okay, then you work with this f of x minus f of x naught divide by x minus x naught minus f of x naught. You try with this. Okay, so this, if you show that this is less than epsilon whenever 0 less than mod x minus x naught less than delta, then this shows that the derivative of capital F at x naught is nothing but small f of x. Okay, so but how will you show this? This is very this is you have to rewrite it. So f of x minus f of x naught. Just now we have evaluated x minus x naught minus f of x naught. So that is equals to 1 upon x minus x time integration x naught to x f of t dt minus, now you can write this f of x naught as 1 upon x minus x naught time integration x naught to x f of x naught dx dt, you can say. The f of x naught is constant. So what it will give you is 1 upon x minus x naught time, you have, this is going to be integration x naught to x f of t minus f of x naught dt. Now use the function, use the factor, now use the magnitude. Okay, so if you use the magnitude, so this is less than equals to 1 upon mod x minus x naught integration x naught to x mod of f of t minus f of x naught dt. Now since f is continuous at x naught, so so this is why mod of f of t minus f of x naught is less than epsilon whenever mod of t minus x naught is means t minus x naught and t is lies between x, right? T is from x naught to x. Okay, so now you are going to use the fact that function is continuous at x naught. Okay, so this will be certainly less than epsilon. Okay, and then this integral will be certainly less than equals to mod x minus x naught. That will get cancelled here. Okay, so now use the fact that, okay, now since f is continuous at x naught, so this implies for epsilon bigger than 0, there exists a delta greater than 0 such that mod of f of t minus, you can say minus f of x naught is less than epsilon whenever mod of t minus x naught is less than delta. Okay, right. So you use this fact now. Okay, and then you can right. So this is less than epsilon whenever mod t minus x naught is less than delta. Okay, and then what will imply? So therefore, you have this is mod of f of x minus f of x naught divided by x minus x naught minus f at x naught is less than equals to 1 upon mod of x minus x naught okay, and how do we work out with this epsilon now? Because this is less than epsilon whenever mod of t minus x naught is less than delta. So t is here is variable. So let's choose mod x minus x naught is less than delta. Such delta only we are going to choose. So this will be still, because t is less than x. So this is going to be mod x minus x naught is so this is certainly true. So mod t minus x naught is going to be less than mod of x minus x naught, right? Whenever t is less than x. So this is, if you choose less than delta, that will work. Okay, so time this is going to be epsilon time integration x naught to x dt. So this is certainly less than epsilon. because this is going to be less than equals to mod x minus x naught, that will get cancelled from here. Okay, right. So this shows that this implies the derivative of f dash at x naught is equals to f of x. So now how means like this will be useful now for you. So if f is continuous at a particular point x naught in the inside interval closed interval ab, then you have this f dash at x naught is equals to f of x naught. So if it is continuous everywhere in the interval ab, so then f dash of x is equals to f of x for every point of x inside ab. And then you can use this capital F as an antiderivative for function f. Okay, so this is where the second form of the this fundamental theorem of calculus gives you. So let f be Riemann integrable and differentiable function f on closed interval ab such that this happens, f dash is equals to f. Then integration a to b f of x dx is equals to f of b minus f of, right? So this is if you replace by f dash of x. So f dash of x dx integration is f of x, right? And if you evaluate at the upper limit minus lower limit will be the final answer. Okay, so one of the case is as follows. So may be a possibility that you may function may or may not be continuous, but you are able to identify a function f such that this happens. That may be a possibility. Okay, right. So like this here. Function is continuous at x naught, or if function is continuous inside a closed interval ab, then this indefinite integral f of x, which is defined by integration a to x f of x dx, okay, is differentiable, and f dash at x is equals to f of x. That's a one of the case. Okay, and let's see how we will apply to the different examples this is. Okay, so in the second form, if you look at it carefully, what are the conditions attached with it is, the very first is f belongs to the class of Riemann integrable. Okay. Second, there exists a differentiable function f capital F on AB such that f dash at x is equals to f dash of x is equals to f small f of x for all x in closed interval AB. Then you have integration a to b f of x dx, which is nothing but integration a to b f dash of x dx, and that is nothing but f of x. Integration of this is f of x, and upper limit minus lower limit give you f of b minus f of b. Okay, so let's look at some example how we will apply this. So first example is, let's say function is mod x. Okay, let f of x is mod x on the closed interval minus 1 2. Okay, so function is continuous, right, everywhere on the interval minus 1 to 1. Okay, so the first form implies that the capital F is defined as integration a to x f of t dt is differentiable. Okay, so here is a is minus 1, so minus 1 to x f of t dt is differentiable. Okay, right. Now it is easy to show that the derivative of this function, so this f dash of x is that signum function. Whenever so this is going to be signum function for x belongs to minus 1 1 and minus 0. You know that this is not differentiable at x equals to 0, but elsewhere it is differentiable. Okay, so f dash of x is signum function of x for x belongs to minus 1 2. So what can you say about this function? So signum function, we have already seen this is a Riemann integrable function, right? This is so small f is means if you want to apply the fundamental theorem of calculus. So for the in terms of fundamental theorem of calculus, your small f, So here is f of x is mod x. Okay, so don't confuse with it. Okay, so what I can do is so for there I will choose the change the notation. G of x is, you can say, function of x. Okay, so which is Riemann integrable. Okay, so this is Riemann integrable. Okay, right. So, and this is you have, this is a capital G of x, you can say, is defined as, so which is Riemann integrable over the interval -1 to +1. So if you define G of x is -1 to x, G of x dx is going to be also it's going to be continuous function. Okay, that is first form of fundamental theorem of calculus. Now signum function is continuous everywhere except at 0, right? So function is this function is differentiable everywhere except at 0. That's we know. Okay, so we don't have, so we are not having g dash of x is equals to g of x for all x in -1 to 1. Okay, so we don't have this. So I can't apply here the fundamental theorem of calculus. So this should be there for the entire interval -1 to 1. Okay, so if you remove the point of discontinuity here, suppose instead of interval -1 to 1, if you consider the interval, let's say 1 to 2 or 2 to 3 and so on, or is the right side of 0 or left side of 0 the part of the interval, you can say. Okay, if 0 is not there, then means okay, that it should be a differentiable at every point. Okay, so small g is Riemann integrable, that's fine, but g is not continuous everywhere. So if g is not continuous, so you cannot have g dash of x, means like is equals to g of x for every x in -1 to 1. Okay, so I can't apply here fundamental theorem of calculus. So that's a summary for this case. Okay, right. Now let's consider this example. What about this here? So let b of x is equals to -x square by 2 if x is less than 0, 1 by 2 x square if x is greater than or equal to 0. Then show that b dash of x is mod x, so that I can leave it as an exercise for you. Okay, so that's because its derivative, you can prove that that's differentiable function and its derivative is modulus function x. Not that b of x is continuous function at everywhere, right? So, right, at x equals to 0 as well, it is continuous function. Okay, so you have, this is, you can say this is your here f of x is mod x, which is Riemann integrable on the closed interval AB, and you have this is f is given by such that, and you have this is f is your b, okay, to b of x, which is such that f dash of x is equals to small f of x, and this f dash of x equals to f of x for every x. So you can apply the fundamental theorem of calculus, and that will give you, that's going to be b of b minus b of a. That you can certainly apply the fundamental theorem of calculus. Okay, right. Now, what about the, I have one more example here. So the example is asking you, can you apply the fundamental theorem of calculus to the following function? So this function is already known among us. This function is continuous. Okay, this is continuous on the entire interval 0 to 1. Not only continuous, it is also differentiable. Okay, that also can be shown. So can be shown that K is continuous. Okay, K is continuous, differentiable on closed interval 0 to 1. Okay, so both properties are here, continuous as well and differentiable function on 0 to 1. So if you find out K dash, what is K dash here? If you find out K dash of X, product rule. Okay, so try to, so one is 2x times cos of 1 by x square. Okay, and another is plus x square, so cos derivative is 9, right? And 1 by x square derivative is minus 2 by x cube, so minus minus plus, so 2 sine of 1 by x square. Okay, so K is continuous and differentiable on closed interval 0 to 1. Okay, so you can differentiate everywhere at every point. So can I apply the fundamental theorem of calculus? We cannot. Why? Because if you look at back the first form of the fundamental theorem of calculus, which says that that indefinite integral, that capital F, what you are trying to identify, that is going to be continuous. So K is continuous, differentiable means K is Riemann integrable. And if you define the capital F for this case, that must be continuous on closed interval AB. Okay, so if a function is continuous on closed interval AB, then it is going to be bounded. But here K dash is not bounded, that function, right, at 0. So if you look at C here, this is not bounded at 2 by x is sitting here. Okay, so this will not be bounded. So hence this is not the fundamental theorem of calculus is not applicable in this case. Now we have all talked about the definite integrals. Okay, and the function is means like is a nice function, means like it is bounded. Okay, on the entire interval -1 to 1, or sorry, a to b. Okay, now there are certain situations, means like you may have the indefinite or you can say the integrals, either one of the limit is infinite, or the function is not bounded on the interval, or the functions whose antiderivative is not easy to find. Okay, it is not easy to find. Okay, so then what will be done is you should approximate that. Okay, you should try to get the good approximation of such integral. Okay, so one of the approximation is already known to you, that is given by Riemann integral. Okay, you just try to identify some tag point, and you can certainly divide the region into n number of rectangles. Sum of their means they can say areas, and that will give you the one of the approximation. Okay, so another approximation technique is given by, instead of rectangle, if you try to approximate the region by using the trapezium instead of rectangle. Okay, that will give you leads to the trapezoidal rule. So if you have the curve here, so it's similarly, if you consider a partition, and draw the vertical lines parallel to y-axis. Okay, and then you create, so then if you join the left hand point or right hand point, that will create some trapezium. Okay, by a straight line. Okay, and you know that trapezium is going to be f of, so if you have, this is going to be f of x naught, this is f of x1, and this is the you can say width. Okay, so that will be, you have, this is going to be, if xk minus 1 by 2 times f of xk plus f of xk minus 1. The ith subinterval of that trapezium, the area is given by this. You know the formula. Okay, and then there is summation k is equals to 1 to n. Okay, so you choose a one interval. So this is one xk to xk minus 1. Okay, and then you have this is the area, and you sum up all the areas. That will give you the sum of all trapeziums. Okay, n number of partitions, n number of you can say n plus 1 number of points you have considered. Okay, so in the same fashion, what we have created the partition. Okay, in the same fashion you can create the partition, and you sum up the area by means of trapezium. That will lead to the trapezoidal rule. Okay, so now just let us consider the equidistant point. So now see here I have not restricted so far the equidistant. So let this let xk, this delta xk, which is not an xk minus 1, is equals to h. Okay, then this implies, okay, so if I denote it by test t n f, that approximation. So the t denotes for trapezoidal rule, f is the over the function for the function f, and n is the number of subintervals you have considered. So that will give you t n of f is equals to h by 2 time. Now you open up this, so you are going to have f of x naught plus f of x1. If you put k is equals to 1, so f of x1 plus f of x naught plus f of x2 plus f of x1, so f of x1 plus f of x2, and so on. So last point is f of xn minus 1 plus f of xn. Now what will it leads to is f of x0 and f of xn will be only once, and intermediate points, at intermediate points you will get twice time. Okay, f of x1 2 times, f of x2 will be also coming to 2 times, f of xn minus 1 will also be in the previous case. So what it will lead to a following rule. Okay, this is going to be the trapezoidal rule. Okay, which is the following formula. So integration a to b f of x dx is equals to approximation h by 2 f of x0 plus f of xn plus 2 times the values of function f at intermediate points, you can. Okay, so you can work with the following example. So with n equals to 4. Okay, so if you want to work with this example, so you have given with the function f of x is equals to x square, and one is 1 to 2. Okay, so a is equals to 1, b is equals to 2. You are given with n equals to 4, means h is equals to what? B minus a by n. So that is equals to 2 minus 1 by 4. So that is equals to 1 by 4. So you have the points are 1, 1.25, 1.5, 1.75. Okay, 2. So 5 points. Okay, and you have, these are the x values. Now similarly you can fix the, and then you can make the f of x values and prepare the following table. So f of x is x square, so 1 square is 1, 2 square is 4, and now you can work with these values. Okay, so you can fill this using the calculator. So I will use the calculator now. And let's complete it. So you have, this is 1.25 into 1.25, that is somewhere like 1.5625. Okay, 1.5 into 1.5, that is 2.5, sorry, 2.25. And you have 1.75 into 1.75, that's 3.0625. So trapezoidal rule says that integration 1 to 2 x square dx is approximately equals to h by 2. So 0.25 by 2 time f of x naught is 1 plus 2 time intermediate value sum plus the last point, that is 4. Okay, so sum of these 1.5625 plus 2.25 plus 3 points, so intermediate values. So this is going to be, you have, this is 1.5625 plus 2.25 plus 3.0625. So that's going to be 6.875. Okay, now this value is equals to, so into 2 plus 5, okay, into 0.25 and divide by 2. So that's equals to 2.34375. So let's give like 2.3428. 2.3438. Okay, and what is the analytical value is, you have, this is x cubed by 3, right? So I is equals to x cubed 3, 1 to 2. So you have 8 by 3 minus 1 by 3. So that is equals to, you have 7 by 3. Right? So it will be something like 2.33333. Now you can increase the number of points now. N equals, instead of n equals to 4, now you can work with n equals to 10. Okay, you create a table, get the approximated value, and you can show that that's going to be converged to the analytical value. Okay, right. Now what will be the error term here? Okay, so the error term by the following formula. And this, for this case, I may give you the hint how do you establish this. Okay, right. Book also have, okay, book also have the same thing. Okay, but it does not use the technique which I'm going to tell you here. Okay, it is using something else that may be more complicated for you. Okay, right. So if you want to show this, you can use the Taylor's theorem. Okay, you can use the Taylor's theorem. Okay, which is so what you do is you can write f of a is equals to f of x plus a minus x times f dash of x, the linear approximation. Okay, by using the Taylor's, and integrate between a to a plus h. Okay, integration a to a plus h, the right side. Okay, and then you can show that this will imply, this should imply, you can integrate this. Okay, and you know how to integrate with respect to x. That's, you can show that integration a to a plus h f of x dx will be h by 2 times f of a plus f of a plus h. So I have considered a general interval a to a plus h, okay, with the length of h. So now instead of a and this, you can take 0 as well, okay, or x0 to x1 or x1 to x2 and so on. Okay, and you can show that error term, if you look at Taylor series, what will be the error term here? The second order derivative. So error term will be a minus x whole square by 2 factorial time f second derivative at some c, okay, where some c lies between a and a and x. Okay, so this you can, so for error term you are going to integrate a to a plus h with respect to dx, so that you can show that this is going to be something like so you will get it, okay, once you integrate everything, and what you will get 1 by 2 more here, okay, you just try to find out, okay, that will lead to that this formula that is going to be minus h cube by 12 times f second derivative x. Okay, so this is a to a plus h. Now a to a plus h, then a plus h to a plus 2h, and so on till b. You can divide and sum up all the error. Okay, so this must be your part of the project. So there you have to write all these details. Okay, you can explore it through Google as well. Okay, the last comment here regarding the Simpson. Okay, I'm going to give you the hint here. So instead of so in the trapezoidal rule, we have only used the 2 points x0 and x1, or you can say x1 to x2 and so on. Okay, and create a by a straight line, and so you know that straight line will use only 2 points, okay, to create straight line. Now instead of straight line, what you do is we are going to approximate it by a quadratic curve. So quadratic curve will be of the possible ax square plus bx plus c of the form. Okay, you are going to fit this. So you have, this is x0. This is your, one way is x0 and x1. This is a midpoint. So you can, so very favorable thing is x0, x1, and x2. You are starting with the 3 points at a time. Okay, and what are these 3 points you can work with is at minus h comma y0, 0 comma y1, and h comma y2. So what is y0, y2 is y0, this is yi is nothing but f at xi. These values, these heights values are nothing but y0 and y2. So you have this quadratic curve passing through these 3 points. So you can certainly get these constants. Okay, and then you just integrate between minus h to h. So try to find out what is minus h to h q of x dx. Okay. That will be, must be, is going to be h by 3 times y0 plus 4y1 plus y2. That you can show that this is going to be the file. Okay, so why we have chosen these points are easy to work. Okay, with these points, this is going to be easy to work. Why? Because we are choosing the 0 as a midpoint. Length of the each side is minus h. Okay, h is the length of the integral. Okay, so it is easy to work with this these 3 points. Okay, then you can generalize the result for any partition. Okay, so then you will get a formula for Simpson's rule. Okay, the formula is already available in the book. Okay, so if you now you can so instead of y0 and y1 y2, now you have this x0 y0, x1 y1, x2 y2, and so on, and then you can work with the formula. Okay, and find out the general formula, or we will state it in the maybe in the next class. Okay, right. Okay. So if you have any question, you can ask.
Sir,
Yeah.
sir, in this Simpson's approximation, we are basically shifting the graph.
Yes. It's
We're taking points as minus h, 0 and h.
Yes.
Okay,
Yes.
sir. Thank you, sir.
Yeah. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah.
Yes.